Hello, my dear bachcho. How are you all? Exams are just around the corner, right? And I can almost hear you thinking, organic chemistry, especially this chapter, alcohols, phenols, and ethers. It feels a bit scary, no?
But bilkul chinta mat karo. Don't you worry at all. Your loving tutor is here, and in the next few minutes, we're going to make this chapter feel like a piece of cake. So, take a deep breath, relax, and let's start.
All right, first things first, let's meet the family. Think of this chapter as a family drama with three main characters. We have the simple alcohols, the very special phenols, and their close cousin, the ethers. Each one has its own personality, its own story.
So how do we call them? How do we name them? It's so simple, beta. You'll laugh. Just think of it like this. Every compound has a common name. That's like your nickname at home, your ghar ka naam, Sonu, Monu, Chintu. And then there's the IUPAC name. That's your official name, the one on your report card, your school ka naam. Simple hai na?
Let's see this in action, okay? Look here, CH3OH. At home, we might call it methyl alcohol, but in school, its proper name is methanol. See? Same for CH3CH2OH. Ethyl alcohol is its ghar ka naam, but its school ka naam is ethanol. And look at this ether, CH3OCH3, dimethyl ether, but its official IUPAC name is methoxymethane. Easy peasy.
Okay, so we've met the family. We know their names. Now let's find out, where do they come from? How are they made? We're not going to study every single method. No. Just the most important ones, the ones your exam papers absolutely love. When it comes to making alcohols, there's one superstar method you must know. It's called hydroboration oxidation. Sounds complicated? It's not. You just start with an alkene. That's a compound with a double bond. Then you add some diborane. And for the final step, you use hydrogen peroxide to oxidize it. That's it. Remember these steps. It's a very, very important reaction. And what about our special character, phenol? How do we make it? Well, there are a few ways, but I'll tell you the easiest one to remember. You take something called a diazonium salt, just warm it up with a little water, and poof, you have phenol. Super easy, right? There's another important one from benzene sulfonic acid, but the diazonium salt method is the simplest. Okay, everyone, pencils down for a second and listen very carefully. The next topic is, I'm not kidding, V.V.I.P. Very, very important, Williamson synthesis. I can almost promise you will find a question from this in your board exam. So, full focus for the next minute or two. So what is this big deal, this Williamson synthesis? Well, it's simply the #1 method that scientists use in the lab to make ethers. And the best part? You can make any kind of ether with it. Simple ones, where both sides are the same, or mixed ones, where the two sides are different. It's like a master key for making ethers. And the recipe is so simple, you'll wonder why it's so famous. You just need two things. First, you take a sodium alkoxide. Think of this as your attacker, your main hero. And second, you need an alkyl halide. But, and this is the most important part of the story, this alkyl halide has to be primary. I'll say it again, primary. And that brings us to let's call it the 10 Lakh Rupee question. The one that examiners love to ask. Why? Why must the alkyl halide be primary? What goes wrong if we try to be clever and use a tertiary one? Think about it. Here's the secret. Our attacker, the alkoxide, has a double role. It's a good attacker, but it's also a strong base. So when it sees a small primary halide, it's easy to attack, and ta-da, we get our ether. That's substitution. But if you use a big, bulky tertiary halide, it's like a crowded street. The alkoxide can't get in to attack. So what does it do? It takes the easy way out. It just grabs a hydrogen from the side and runs away. That's elimination, and we end up with an alkene, not the ether we wanted. So the golden rule is, for Williamson's recipe, you need a primary alkyl halide, full stop. Brilliant. So we know who they are and we know how to make them. Now let's see how they behave. We'll look at their most important chemical reactions, again, focusing on the ones that are exam favorites. Let's imagine a fight, an acidity battle. In one corner, we have alcohols. In the other corner, we have phenols. Who do you think will win? Who is more acidic? Well, it's a total knockout. Phenols are the clear winners. Alcohols are actually very weak acids, even weaker than water. But phenols, they are much, much more acidic than both alcohols and water. But
Why?
The answer to why is always in one word, my dear children: stability. It's all about stability. Look, when a phenol loses its proton, its H+, it becomes something called a phenoxide ion. Now, this ion is super, super stable. Why? Because that negative charge isn't just sitting on the oxygen atom. It goes for a walk around the whole benzene ring. This is what we call resonance. And if the product is stable, the reaction happens easily. So phenol is happy to give away its proton, which makes it acidic. Now for a super tip, beta, a pro tip. We just said stability is the secret, right? So what if we can make that phenoxide ion even more stable? How? By putting an electron withdrawing group, like a nitro group, an NO2 group, on the ring. This group pulls the negative charge towards itself, spreads it out even more, and makes the ion super duper stable. And more stability means, you got it, even more acidity. Okay, another very famous reaction. This is one you will definitely do in your school lab. It's a test for phenol. The question is, what happens when you take some phenol in a test tube and add bromine water to it?
The result is instant magic. The second you add the bromine water, you will see a thick white solid, a precipitate, form right away. This white stuff is 2,4,6-tribromophenol. And why does this happen so fast? Because that OH group on the phenol makes the benzene ring super active, almost hyperactive. It just reacts with the bromine instantly. This is the confirmation test for phenol. Remember this.
All right, we're almost at the end. For our last section, let's talk about something really important, something that connects to our real lives. Because, not all alcohols are the same. There's a good one, and then there's a very, very bad one. So let's meet the two most famous members of the alcohol family. First, we have ethanol. This is the one made from fermenting sugars, like from grapes. It's used in industries as a solvent, and it's also the type of alcohol found in drinks. Then we have its cousin, methanol. This one is also called wood spirit, and it's used in things like paints and varnishes.
Now, this is the most important thing I will tell you today. Please listen. While they sound similar, ethanol and methanol are completely different. Methanol is dangerous. It is highly, highly poisonous. Just a very small amount can cause blindness, and a little more can even cause death. So please never, ever confuse the two. This is so, so important to remember for your entire life.
And that's it. We did it. See? Was that so hard? Not at all. We covered everything important. The names, how to make them, the superstar Williamson synthesis, and the most important reactions. You guys are champions. I am so proud of how well you've listened. You are going to rock your exams. I know it.
But before I let you go, I want to leave a little question in your brilliant minds. We just learned that adding a nitro group makes phenol more acidic. What if we add 3 nitro groups to a phenol? It becomes a very, very strong acid, right? But here's the twist. That same compound is also a powerful explosive. Any idea what it's called? Go find out. All the very best, my dear children. You can do it.